Okay, so today we'll see magic T, scattering matrix of my magic T. So magic T, it is also called as EH plane T, or it can be even called as hybrid T, or it can even called as magic T. Okay, so it is a combination of both your E and H plane, E plane and H plane. Okay, it can even be called as 3 dB coupler. And here port 1 and port 2 is your collinear arm, port 3 is my H arm, and port 4 is my E arm. So E arm can be called as a difference arm, and this H arm can be called as sum arm, right? So this is my H arm is my parallel port, and this is my series port. Okay, so now because it is having a 4 port network, so we can write a square matrix like 4 cross 4, right? So I can write my S matrix, it is of order n cross n, so 4 cross 4, and my S parameter, so what are the possible parameters? I can have 16 parameters because it is having 4, right? So S11, S12, S13, S14, S21, S22, S23, S24, S31, S32, S33, S34, S41, S42, S43, S44. So like this I can write my matrix. And here, because it is having both combination of both your E plane as well as H plane, right? So it should satisfy both H plane property as well as E plane property, right? Right. So when I say it is satisfying the E plane property, this property E plane property, so E plane property I have given the number as 4, port number as 4. So when it is satisfying the E plane property, I can say S14 is equal to S2 in magnitude but opposite in phase, right? So S14 is equal to minus S24. Same way, if it is satisfying the H plane property, I have given port 3 as a H plane, so I have to say S13 is equal to S23, right? So this all we will see in your H plane matrix. Okay, so that is what it is given here. And one more thing, so because of the geometry of the junction at input of an input at port 3, right, if I give input at port 3, it will not be able to come out from port 4 because your port 3 and port 4 is isolated, right? Same way, if I give input at port 4, it will not get it at port 3 because it is isolated. So I can say my S34, it is equal to S43 equal to 0 because this 3 and 4 is isolated. Same way, my port 1 and 2 is also isolated. Okay, if the signal is fed at one collinear port, then the 3 appears no output at the other collinear port. So I can even say S12 is equal to S21 equal to 0. So this is the important magic of the T, right? Even S12 and S21 is isolated, S34 and S43 is isolated. It means if I give input at port 3, I will not get it at port 4. If I give input at port 4, I will not get it at port 3. If I give input at port 1, I will not get at 2. If I give input at 2, I will not get at 1. So 1, 2 is isolated, same way 3, 4 is isolated. Okay, and now we will substitute all those things in the matrix, right? So you know what is the matrix, and for your magic T, your port 3, if let us assume your port 3, if port 3 and port 4 both are perfectly matched, we are assuming that, okay? So normally match condition is complex here. Suppose if you assume that port 3 and port 4 is perfectly matched, I can write S33 is equal to S44 equal to 0. Okay, and the symmetry matrix, you know, Sij is equal to Sji, so S12 will be equal to S21, S13 will be equal to S31, S14 equal to S41, S23 equal to S32, 24 equal to 42, 34 equal to 43, likewise. So I will substitute all those things, and finally I am getting a matrix like S11, S12, S13, S14, S21, that is 1 2, S22, S13, and here 2 4 S24, that is your property of your E-plane. So I'll write S14, S13, S13. Here I said your S3 is equal to S44, right? So this is 0 and this is 0, and here S14 minus S14, and what is this? S43 equal to S44, this is 0, and that is your perfectly matched port is 0, and because it is having the isolated port, this is 0. So this becomes my matrix now. And also I know your S12 and 21, this will also be equal to 0, right? So now let us keep like this only, and the next properties I have to multiply this with its complex conjugate, and what I'll get if I do that, so I'll get row 1 column 1, that is equal to, from this equation, this is my matrix, I have to multiply this with its complex conjugate. So I'll get S11 square plus S12 square plus S13 square plus S14 square equal to 1. Same way if I do for R2C2, I'll get S11 square plus S122 square plus S13 square plus S14 square equal to 1. Same way if I do for R3C3, I'll get S13 square plus S13 square equal to 1. If I do it for row 4 column 4, S14 square plus S14 square equal to 1, right? So now from these two equations, from this row 3 column 3 and row 4 column 4, I can solve for S13 and S14, right? S13 is equal to 1 by root 2 and S14 is equal to 1 by root 2. And comparing these two, R1C1 and R2C2, if I compare, S11 will get cancelled, S13 will get cancelled, S14 will get cancelled. So I will have S11 equal to S22. Okay, and substituting this S13 S14 in the first equation, if I substitute in this first equation, I'll get S11 square plus S12 square plus 1 by root 2 square plus 1 by root 2 square equal to 1. So this is 1 by root 2 square 1 by 2, 1 by root 2 square 1 by 2, so 1 plus 1, 1 by root 2 plus 1 by 2 plus 1 by 2, it is 1. So if I take this side, that will be equal to 0. So S11 square plus S12 square equal to 0. So S11 equal to S12, I can write like this. And from this equation and this equation, I can say S22 is also equal to 0. So that is why if I substitute here, S11, S12, S21 and S22, this is all equal to 0. Okay. So finally, after substituting all the equations, I will get like 0 0 0 0, 1 by root 2 1 by root 2, 1 by root 2 minus 1 by root 2, 1 by root 2 1 by root 2, 1 by root 2 minus 1 by root 2, 0 0 0 0. So this will be my matrix. So here they have taken 1 by root 2 outside. Okay, and if I want to find out that equation, I will get, I can write no. So B is equal to S into A. I can write, so I will get B1 is equal to A3 by root 2 plus A4 by root 2, and B2 is a3 by root 2 minus a4 by root 2, and my b3 it is a1 by root 2 plus a2 by root 2, and my b4 is a1 by root 2 minus a2 by root 2. So I have all these four equations. So I have to solve it for different conditions. So you can solve it for different conditions. I am just giving you the conditions. So for case 1 you take a3 is not equal to 0, a1 equal to a2 equal to a3 equal to a4. So this is all equal to 0. And case 2 you take a4 is not equal to 0, a1 equal to a2 equal to a3 equal to 0. So this will satisfy my H plane property, this will satisfy my E plane property. You have to check all this thing. And third property I can take a1 not equal to 0, a2 equal to a3 equal to a4 equal to 0. So in this condition I will get that isolated ports, right? Same way take for another case, a3 equal to a4, a1 equal to a2 equal to 0. So here this will satisfy the additive property. And one more case also you can take, fifth case, a1 equal to a2 equal to 0, no, equal to a, keep it equal to a, right? a3 equal to a4 equal to 0, right? So if you solve, if you keep that conditions and if you solve for different criteria, what is happening? So this is what you have to check for your H plane. Okay, so here you have taken a3 equal to a4. Here I will take a3 a4 as 0. Here I have taken a1 a2 as 0. I will take a1 a2 as equal, and you solve. Okay, and next is the application. So application of your magic T, it can be used as a bridge for measuring your impedance, right? And it can also be used as duplexer. So duplexer, it is working as both transmitter as well as your receiver. Because we have a single antenna, it can that is your port 1 and port 2, that is used as your receiver and transmitting antenna. Because we have that isolated property, it will not interfere. So that will all check. So because of that only we are using this in the duplexer. And same way we can use this as a mixer, because I have that property, right? EM property and H property, addition and summation, summation and subtraction, right? So you can see whether it is satisfying that property. So your magic T can be used for measuring impedance, it can be used as a duplexer, and it can be used as a mixer. So that's all about your magic T.